we discuss the main thin film technologies that are treated in this course. In this section, we will discuss some concepts that are important for more than one of these technologies, such as the deposition sequence, transparent conductive oxides or TCOs, and the multi-junction concept. We will start our discussion in this video with the difference between the substrate and superstrate deposition orders. The other learning objectives for these videos are the function of the TCO in a thin film solar cell and the material properties and performance of TCOs. Finally, we will consider the materials used for TCO production. We see here a superstrate and a substrate solar cell. The difference between these configurations is the deposition order. For the superstrate configuration, a transparent superstrate, usually glass, is used. The semiconductor junction and metal electrode are deposited on top of the glass substrate. This means that the layer that is first passed by the incident light in the solar cell is also deposited first in the solar cell. Alternatively, in substrate configuration, either the substrate acts like a back contact or the back contact is deposited in the substrate. Consequently, no light will pass through the substrate, and light first encounters the layer that is deposited last. As you will see in the upcoming video lectures, a PV module based on CIGS has a substrate configuration, while a thin film technology like amorphous silicon on glass usually has a superstrate configuration. No matter the deposition sequence, thin film solar cells generally require the use of a TCO layer. As we well know, charge carriers generated in the absorber layer are separated and collected at the front and back electrodes. If we assume the P layer to be at the back side of the cell, holes are collected at the back electrode by recombination with electrons supplied by this electrode. The back electrode covers the entire surface of the solar cell. The front electrode, collecting the electrons, however, only covers a very small portion of the front surface. In order to minimize shading losses, many materials used for thin film solar cells have relatively poor lateral conductivity due to the thin film deposition techniques and growth direction of the materials. Thin film cells therefore require a highly transparent layer with good lateral conductivity. There are several materials that could act as such a transparent front electrode. We can consider, for instance, the use of a very thin metal sheets of only a few nanometers thick. The transmitted of such a metal sheet is plotted in this graph as a function of its resistance. The metal film becomes less transparent and more conductive as the thin film thickness increases. The same trade-off between the conductivity and transparency is observed in carbon nanotubes. The performance of carbon nanotube is, however, up to now much lower than that of other materials available, such as transparent conductive oxides. Transparent conductive oxide follow the same trend of the transparency versus sheet resistance, but their performance is much better. A transparent conductive oxide, or TCO, is a metal oxide mixture with a wide band gap. As we can see, the optical and conductive properties can vary quite a bit. These properties depend on the nature, number, and the atomic arrangements of the metal particles in the material and on the presence of defects. The defects can be intrinsically present or purposefully introduced by doping of the material. Let's look at the TCO material properties in some more detail. Shown here is the optical performance of an aluminum-doped zinc oxide layer with a thickness of 880 nanometers used as front transparent electrode. The red area represents absorption and the yellow area represents the reflection by the layer. Blue indicates the transmission through the TCO. We can divide the spectrum in three parts. For short wavelengths, the photon energy exceeds the TCO bandgap energy, leading to very high absorption by the TCO layer. For energy below the band gap energy, the transmission through the TCO is very high. In this part of the spectrum, we can see the interference fringes of the TCO layer that can be used to determine the layer thickness. After a broad, highly transmissive wavelength band, the absorption increases again. This absorption is called free carrier absorption and can be explained with the Drude model of metals. The Drude model of metals will be discussed in the next video, where we continue our discussion of transparent conductive oxide layers.